Hi, everybody. So today I wanted to talk a little bit about some different bond types, pretty much wrapping up of covalent bonds, talking a little bit about polar covalent bonds, and then spending a little bit of time on the next kind of bond, which is the ionic bond. So I'm going to draw a couple of pictures, show a couple of diagrams, and hopefully that'll clear up any questions that we might have about these different bond types for the assignments that we'll be doing. So I'll do a brief little recap of covalent, talk about the difference between polar and non-polar covalent, and then talk a little bit about ionic and show you an example or two of that. So we already sort of understand the basics of covalent bonding, and I'll just do an example of covalent bonding with like carbon because it's super useful in the biological sciences. Let me pick a good pen color here. So here's our carbon nucleus with 6 protons on it. So here's our first 2 in the inner shell, and then, 4 more. 1, 2, 3, 4. And we oftentimes think about what are the simplest molecules that we can draw to demonstrate a concept. And for carbon, I'm going to use it's called methane. The molecule I'm drawing right now, do the off at the top, it's CH4. So what I can do, I can take a proton right here, or a hydrogen ion or hydrogen atom, nucleus, shell, the carbon shell right there, and covalent bond. And I can do that again here. I can do that again here. And I can do that again here. And here's my 1 proton nucleus, my 1 proton nucleus, 1 nucleus, 1 proton nucleus, 4 hydrogen. So here's the carbon right there and the 4 hydrogens around it, just like that. So how does this, let me fill in my shell, how does this fit that kind of guideline that we were talking about before, that octet rule? We were talking about how a lot of things, not all, a lot of elements in that second row in the periodic table follow the octet rule, where they become most stable when there are 8 electrons in the outer shell, or the equivalent either by what they currently have or by sharing. So if we think about carbon, with its native 4 valence electrons, we have the 4 additional ones that we get, 1 from each of the shared ones from the hydrogen, which takes us up to 8. So 1, 2, 3, 4, 5, 6, 7, 8. Likewise, hydrogen has 1 proton. That first innermost shell can hold 2 electrons, and so that sharing works for each of the hydrogens as well. 1, 2, 1, 2, 1, 2, 1, 2. So, hydrogen is acting like its outer valence shell is full, nice and stable, non-reactive. The carbon is acting like its entire valence shell is full, stable, not reactive. Everything is good. We have stable methane. Everything is great. 4 covalent bonds. Perfect. Let's give this a quick little erase. And I want to talk about then the difference between polar and non-polar covalent bonds. Bonds of the covalent sort are non-polar when electrons are shared equally, which means they are polar when the electrons shared, it's a D, unequally. So a case where you would have equal sharing would be in something like hydrogen, because what's going to cause the inequality, if there is unequal sharing, would be a difference, I don't know if I spelled that right, in It went off the screen. Difference in electronegativity. Perfect. So electronegativity, defined, is essentially the ability or the propensity or the property of an element to pull electrons closer to itself when they're being shared. So if you have two of the same element with the equal electronegativity value because they're the same thing, right, then when they share those electrons in a covalent bond, they're going to share them equally because they're both pulling on the shared electrons with the same amount of force, or with the same strength. So what I would do right now, I would show you this wonderful picture, this diagram, if you will, of the periodic table with the electronegativity values shown as numbers. And here you can see some of the different numerical values associated with different elements in the periodic table. And this other diagram, which I really like a lot, which is a third axis. So we have the periodic table as it's laid out, but on the third axis, like a height axis, we can see the height of each one of the elements is kind of raised to the degree of its electronegativity value. So what you see is the most electronegative atom out there, the most electronegative element, is fluorine in the upper right of the periodic table. The least electronegative elements are these down here in the lower left, the francium, the cesium, things like this. And so that you might be able to see a general trend. Electronegativity increases as you go from left to right and from bottom to top. So the most electronegative elements are in the top right. The least are in the bottom left. So what we can do then, we can compare those electronegativity values when we have two elements combining in a covalent bond. And that will end up looking like this. One of my favorite electronegative elements that we use in biology a lot, and this will be actually a property that we use when we talk about respiration and all the things that mitochondria do, obviously, is oxygen. And so if I can draw one, here's using our conventional way that we draw things as 8 protons in the nucleus. Here's the 2 inner shell, and we have 1, 2, 3, 4, 5, 6 left over. And we just draw another one because we're going to make O2, molecular oxygen that's bonded to itself. Nucleus, 1, 2, and then 1, 2, 3, 4, 5, 6. And its outer shell and the outer shell of this over here. A covalent bonds that we would draw there and there. Awesome. So is this a stable molecule? The answer would be yes, if the valence shells act like they're full. So 1, 2, 3, 4, 5, 6, 7, 8 for both. So it's acting like the outer shell of the valence shell is full, so it's a pretty stable molecule. So they both have pretty high electronegativity values. Their value is about 3.5 for both of them. So it's pulling pretty hard on the electrons, but it's pulling very evenly. So the electrons are still kind of housed right in the middle. There's no weird like overpowering of one element over another and anything like this. If the electronegativity values are the same between bonding partners or very close, we say that it is a non-polar covalent bond. Make sense? Does that make sense? An alternative would be if you have a covalent bond between two bonding partners and their electronegativity values are very different from each other. If that's the case, then we have polarity in the bond, and therefore we have polarity in the molecule as well. So a good example of this would be between hydrogen and oxygen. So if I can draw, here's our oxygen molecule. I was using pink. 8 protons. There's our nucleus, inner shell, And I'll just draw a water molecule since we're familiar with that. Okay, here's our oxygen. Electrons, great. Here's one of our protons or hydrogen ions and a covalent bond, and there's the other one. Classic water molecule, nothing too strange here. We've drawn this before. The electronegativity value of oxygen is about, like we said before, 3.5. For these hydrogens over here, it's a lot lower. It's about 2.1, give or take. It's pretty low, right? So when there's a bond here forming between hydrogen and this oxygen, the oxygen nucleus is pulling really hard on this pair of electrons, and they're really getting pulled quite strongly over in the oxygen direction. So if we wanted to draw these electrons a little more accurately in the context of what this bond is doing, we would probably go something like this. So there's one, there's the other, there's one, there's the other. So the electrons are being pulled closer to the more electronegative one. So if we draw a line here on this side of the molecule, the oxygen is acting like it's having more electrons than this side is because it's pulling the electrons from the hydrogen over closer to it. So this is like it has extra electrons over the number of protons. So if it's like 8 protons, if you count the electrons over here and you're counting these a lot, it's almost like it's got 10. So there's going to be a stronger negative association with this side of the molecule. Likewise, this side, it's all protons and no electrons at all because they're getting pulled over here. This side is more positive. So we would say this is a polar covalent bond. Polar covalent bond. Water, excellent example. The more the difference in electronegativity between the bonding partner, the more polar the bond is going to be. Very good. So that is polar and nonpolar covalent bonding. And I might just kind of leave it at that right now and separate this into 2 videos, just to kind of keep them a little bit separate if you'd like to. So please let me know if you have any questions about this one, and I'm happy to have a chat. Thank you.